This is a lightning talk, so it's a short talk. And I will be talking about the design choices with respect to OpenSSL based on the automated analysis that it's already running CROCS, so the group that I'm from, Center of Research and Cryptography and Security at Masaryk University, Brno, is conducting these different types of analysis like that for, let's say, last 10 years. And of course, therefore, this is a joint work with a lot of people. I will not list them now. So maybe first, let us mention how this approach works. So what do we do? Of course, as let's say a joke, on the right top corner, we see gnomes. They collect things, they do something, and then at the end, they obtain some sort of profit. So our approach will be similar. All this analysis that we do is we collect a lot of data. We are searching for some anomalies. If we find, or when we find an anomaly, then we dig more there. So our targets are not, of course, underpants. This will be various cryptographic targets. So the process in detail, how it would look, we will design technique to probe a cryptographic target. It's usually very comfortable to do it on some open source implementation to be able to, let's say, verify whether our technique works. This is just a technique to probe the behavior, search for biases. We implement some open source tool for testing, so to be able to publish it, perform tests on a wide range of targets, including especially closed source targets like smart cards, but also open source ones. And then when we spot biases, then we try to develop an academically publishable exploitation method. Ideal outcome, method can be published. There is real-world impact. So actually step 4 succeeded. So we were able to exploit something. And then an open analysis tool together with the exploit ultimately will be published, and these things can be used by us later on or by future in general in research. And through that process, we gained insight into a lot of implementations, and I will detail in a second, including OpenSSL, and develop multiple tools. Here I give a link, but I will also give at the end a QR code, and there will be a lot of links. Because again, this is a talk with a lot of research going there. So there will be three short parts of these slides. I hope it's visible, but here essentially there are a lot of open source libraries on the left. So we always analyzed all of them, including here OpenSSL. And here on the other side, we have closed source libraries, usually in form of smart cards, but not only. We looked at different things too. Then we do our question mark, so we do something, and then we get some insights. So to summarize, which things we did? Number one was analyzing RSA keepers. So we generated millions of them, and we searched for biases. This resulted in insights that I will share in a second, and also a vulnerability. So it occurred that some implementation was actually purely insecure. So that's first thing. I will detail a bit more in a minute. The second approach was to analyze pretty much all open source crypto libraries with respect to ECC, analyze how many different types are there, search for some interesting things. This resulted, again, insights, reverse engineering tool called pyecsca, and this work still continues to this day with next works. And the third thing that I will mention is, again, the same approach. We are collecting ECC operations, so ECDSA timings, and we run a mass analysis. So if you read the paper especially, it might look to you like we, let's say, found one library, we analyzed it, we found issues. That was not the case. It was run on scale. We found bias, and then we dig deeper into that. That resulted, again, in some insights that I share, Minerva vulnerability, and the tool that is called ECTester. Okay, so let me go to the RSA keepers. RSA is essentially the private key is P and Q, so 2 prime numbers, and then there is modulus. I'm not going here too much into detail, but you can imagine that you can start running some statistic. For example, on the two most significant, on the most significant byte, essentially, of both P and Q. So let us imagine that we have our OpenSSL. library. So, okay, this is a bit older version, but what you can see is that if on x-axis you have most significant byte of P, on the most significant byte of Q is on the y-axis. If you plot it, you can see that if it was completely random, you would expect everything. This is a heat map, so you would expect the color everywhere. Here you can see just some sort of triangle. This is not at all a security vulnerability. But what's interesting is that when you plot in this example, 6 different crypto libraries, you can see that that's OpenSSL, that's Microsoft Crypto API, and essentially every crypto library has different pattern. This is under assumptions that we know the private key, we know P and Q, so this is, let's say, not big surprise. But the whole work aimed at figuring out such a biases already from the public key. And you can imagine that even if you have public key, that is the multiplication of these two numbers, there might be some interesting biases in that value. So that work resulted in 7 implementation choices observable in public keys. It also got the best paper award at USENIX 2016. So first observation, information leakage. We can recognize OpenSSL key generation from public key. And then based on that, you can run a whole scan and classify how many OpenSSL keys are in the field, how many Microsoft Crypto API keys are in the field, and essentially we did that analysis was done in the past, and this was interesting. It also resulted in more interesting things. So let us imagine that there is an organization that tells we only use key generated on certified smart cards. And you test the whole, you can test it using this tool, and it occurs that yes, 95% of the keys are generated using that device, but not all of them. And then there is a question, what happened? Because it clearly shows that someone is using differently, let's call less secure keys. And most importantly, it resulted in a real vulnerability, so it resulted in finding out and reverse engineering and ultimately exploiting vulnerability in one of the crypto libraries used in certified smart cards. That was already quite some years ago, so maybe not everyone heard about Roca vulnerability, but that's what happened. I will not go now more into detail. If you want, please ask me later. And first, let me go through everything else that I have. Another approach, we looked at all the cryptographic implementations that we found in the field. The main conclusion from that, as expected, was that this ecosystem is a wild jungle of different implementation choices with curve models, coordinate systems, addition formulas, etc. It totaled to 140,000 implementation choices. We documented OpenSSL and everything that we analyzed on the pyecsca website. So that's the name of the tool that we used. If you click on the link, you can find everything that we found there. OpenSSL provides wide range of implementations with different types of formulas. And in general, what we also found out that it has great value for us because it's open source, auditable, it is certified, and that's contrary to almost, okay, let's say most certified products that are closed source. So very often in certification, there is plus to have closed source, and that's also a chance for us to find issues. And then if you use the QR code provided there, then you can go to the paper and see, for example, which elliptic curves formulas are implemented in OpenSSL. I mark here it on the link, on the picture. Additionally, you can see which libraries share which implementation choices, but let's say it's useful for reverse engineering mostly, I think. Let me go to the third topic that I wanted to cover, so measuring elliptic curve operations time, ECDSA. We will be looking at the most significant byte of the nonce with respect to the execution time. And then what's known from math is if you can find some bias in the even most significant byte of the nonce, then you can recover the private key. So you can see the nonce as the private key. So let me go for that. We run it on OpenSSL. This is essentially different values of the nonce, so from 0 to 256. And this is a heat map showing how long is the execution time here. And we can see that there is a flat line here. So essentially that it's it's a straight line. So there is probably not that much. So it tells us it's constant time, it looks fine. This thing was run on multiple of the libraries, including Bouncy Castle, again, something like straight line. In the papers, everything is documented and you can analyze. But what was interesting is, again, for some closed source library, there is something like that scene. So what that could mean? Again, this is 0, this is 256 on the other side. So we can start perhaps labeling the traces. So if the most significant bit is 1, then the execution is longer. If it's 0, 1, then it's a bit shorter. And the more zeros you have in front of the nonce, that is used as a scalar, the shorter execution time. And that resulted in the so-called Minerva vulnerability, and that was done using the tool called EC Tester. Okay, so with respect to these main observations or insights, I did cover everything, and now I just wanted to mention a few things about the tooling, because for us it's also the value in everything that we put open source. So the first thing is pyecsca, that's used and it's still being used for analyzing of ECC implementations. Then there is EC Tester. Ultimately, it's used for similar goal, but we also work on much more tools. Here I mentioned JC Profiler Next. So the JC Profiler Next, that's a tool for timing analysis of Java card in code. Additionally, what I wanted to mention is pyecsca can be also used for the analysis of physical side channel traces. So if you have a real oscilloscope, you can measure power or EM emanations. Then you can also use it for that. Here I put also a link to the tutorial if you want to experiment with that. And it more or less looks like that. So you can, maybe it's not super visible, but you can plot an execution trace. And in this example, there is some simple analysis done on counting how many peaks occur there in the trace. And not perfectly visible, but we counted 254 iterations of something. That very often will suggest that we are looking at X25519 protocol, because that's usually the number of operations there for Montgomery ladder. But this is just, let's say, a short advertisement. To summarize the talk, here I very briefly talk about automated and large-scale testing of cryptographic implementations. I presented different insights for OpenSSL and also very briefly, various RSA or ECC issues that were discovered. Again, I would like to underline the importance of open source and auditable implementations, especially in the certification context, and the importance of open source tooling for this sort of research. So here are some links to the tools that we are developing and using, and to the website of our group with the QR code if you are curious about any of these toolings, to have a look. So it's time for questions. Here there are also 2 more talks given by tomorrow by people from affiliated with the Crocs Lab. By Waszek Matyas, Martin Ukrop, and Vladimir Penas. It's somehow usually related to certification, another area that we do much research. And then I think there is some time for short questions.
Thank you, Łukasz. We have time for a really quick question, if there is one.
The heat maps you've shown, the key distributions, I didn't fully get what the heat maps display, but as the keys are hopefully drawn from uniformly at random sources with enough entropy, shouldn't they all look the same?
No, because they are actually, when you read the algorithms that generate the prime numbers, this is usually when you read how RSA is done, you hear uniformly at random, but even that's not the case. There are some conditions. There are types of prime numbers that there exist faster algorithms. So they always do things like, you can see what's happening in practice. Like, for example, setting the most significant bit to 1. That's happening. But additionally, the fact that it's not mirrored that's okay because it's symmetrical. But also you can notice that there are some zeros. There are various reasons. There are various algorithms that do it efficiently. These are algorithms for smart cards. If you don't want it to run 20 seconds, so there will be some small optimization things, and there are papers about it that describe it there. But then it occurs that everyone, like it's not like people use the same algorithm. They use different algorithms, and that's why the issue was happening. It was strongly optimized, and someone went too far. They optimized it so much that it became insecure.
Thank you. Thank you again.